Hello everyone, this is Om Prakash from CSIT. My topic is about instrument transformers. Instrument transformers are two types: CT current transformers, current scaling isolation; VT voltage transformation, voltage scaling isolation. Current transformers. Current and voltage transformers are responsible for scaling primary system signals. Typically, nominal secondary values are 5 amperes and 1 ampere for current transformers and 110 voltage for voltage transformers. Conventional magnetic current and voltage transformers are still in wide use in power systems. For voltage levels greater than 230 kV, we substitute capacitive coupled voltage transformers CCVT for VTS CT saturations and bad transient response of CCVTs create potential problems. New trends in current and voltage transistors are low power output current and voltage transformers recently included in IEC standard, and magneto-optic current and voltage transistors MOCT and MOVT. MOCTs use the Faraday effect and MOVTs can use either the Faraday or Pockel's effect. Principles of current transformers. The initial problem was how to connect a low voltage device to high voltage system and have the ability to handle large fault currents kiloamperes. How can we make the really measure the currents flowing in the high voltage system in order to detect these faults? The solution consists of using a special type of transformers called a current transformers. The main part of a current transformers are iron core, secondary winding, primary conductor, external insulation. Some current transformers don't have a primary conductor. In those cases, the primary is the line bus itself. Sometimes the core and its secondary winding are directly installed in the bushing of the circuit breaker or transformers. These CTS are called bushing CTS. Some current transformers may have a primary that consists of several turns. Typically, there are no more turns than the natural, which is equivalent to say that the primary number of turns is 1. The total load connected to the CT terminal, G and H in this case, is called burden. Ideally, the secondary current of a CT is perfectly proportional to the primary current. It will be shown later than the reality that this is sometimes not true. These are example for core and secondary winding, and this is example for high voltage CT. CT symbols. Note that in all cases there are polarity marks. The following conventions are used to mark the references for AC currents. ANSI polarity marks: IEC, P1, P2, S1, S2, VDE, KL, KI. CT common connections. Y delta. These are two of the most common connections of the current transformers in three-phase system. At the left, the Y connection provides the line current at the secondary. At the right, the delta connection provides the difference currents, delta currents, to the secondary load. Current transformer ratio CTR. The current transformer ratio CTR expressed as fraction is the ratio between the magnitudes of the primary and the secondary current for either working conditions of the current transformers. CTR formula: CTR equals to IP by IS. Denominator is the secondary rated current, typically 1 ampere or 5 ampere. Numerator is IS, not always the primary rated current. IEC standards accuracy classes. The IEC means International Electronical Commission specifies current transformers as. This is the diagram of current transformer equivalent circuit. CT performance calculations. The performance of a CT may be found from two approaches. First one, the formula method, another one is the saturation curve method. Formula method: core parameters ES equals to 4.44 into NS into F into pi naught M. ES equals to 4.44 into NS into F into BM into A. Es equals to voltage V, Bm equals to maximum flux density Tesla, F equals to frequency Hz, A equals to core area m square, Ns equals to number of secondary turns, pi naught m equals to maximum flux Web. Second, the saturation curve and error method. The relation between ES and IE is not linear like the relation shown in the figure 1. Due to the saturation of CT core, therefore the CT has a ratio error. Figure 1, magnetizing curve. The deviation of I'(S) from Is is called the CT error and can be expressed as percentage CT error equals to Is minus I'(S) by Is into 100% equals to IE by Is into 100%, where Is minus I'(S) equals to IE. Is means total current in the CT secondary, I'(S) current due to the CT load. Example: assume that a CT has rated current ratio of 500 by 5 amperes. The impedance of the secondary winding Z2 equals to 0.242 ohms and the burden impedance ZB equals to 0.351 ohms. The core area A equals to 0.00193 m square. The CT must operate at maximum primary current of 10 kiloamperes if the frequency is 60 Hz and the core is built from silicon steel. A. Determine where or not the CT will saturate. B. Determine the CT error. Solution: Is equals to 10,000 into 5 by 500 equals to 100 A. If we neglect the excitation current, that is I dash similar, Is equals to 100 A. Es equals to Is into Zb plus Z2 equals to 100 into 0.351 plus 0.242 equals to 59.29 volts. Es equals to 4.44 into F into N2 into A into Bm. So Bm equals to 59.29 by 4.44 into 60 into 500 by 5 into 0.001935 equals to 1.15 T. As we know that the lower limit of for the silicon steel saturation is Bm equals to 1.2 T. Hence the CT will not saturate. From the saturation curve, the corresponding IE for ES equals to 59.29 volts is IE equals to 0.1 A. CT error percentage equals to IE by Is into 100% equals to 0.1 by 100 into 100% equals to 0.1%. Saturation curves for silicon steel used in current transformer core for different CTRS. CT classes and accuracies. Accuracy class 0.1, 0.2, 0.5, 1.05p, 10p. Percent error plus or minus 0.1, plus or minus 0.2, plus or minus 0.5, plus or minus 1.0, plus or minus 1, plus or minus 3. Applications: metering protection. CT specifications: a rated burden at rated current or volt amperes. And accuracy classes: ALF, accuracy limit factor and upper limit behind which the accuracy is not guaranteed. Example 1, 15 VA classes 0.5 metering CT. Example 2, 15 5P 20 protection CT. Rated burden 15 VA, accuracy class 5P, ALF equals to 20 times the rated current. Voltage transformers. Voltage transformers are connected across the points at which the voltage to be measured. Types of voltage transformers. There are three main types of voltage transformers. Magnetic voltage transformers, ordinary two-winding type used for LV and MV. Capacitive voltage transformers, CVT, used for high and extra high voltage. Magneto-optic voltage transformers, new. Magnetic voltage transformers, VT. This is diagram for magnetic voltage transformers. Ideally, Vs by Vp equals to Ns by Np. VT equivalent circuit referred to the secondary side. This is ideal transformer circuit. Capacitive voltage transformer, CVT. There are two types of CVTs: coupling capacitor voltage transformer, capacitor bushing voltage transformer. These types are shown in figure below. Figure A is the coupling capacitor voltage divider. Figure B is capacitance bushing voltage divider. This is CVT equivalent circuit. This is HV terminal capacitor divider, and this is electromagnetic unit EMU, and this is voltage divider capacitor. This is P1, and here electromagnetic unit, and this is secondary unit. This is the diagram of CVT equivalent circuit. This is the diagram of line voltage, L compensating reactor, step down transformer, relay voltage. VT error. Errors in magnitude can be calculated from error VT equals to NVS minus VP by VP into 100%. Table voltage transformers error limits. And this is the voltage transformers error limits. These are the voltage connections: open delta connection, delta Y connection, YY connection. This is my small presentation. Thank you for giving this opportunity.